I will change my plan slightly. So, I want to look at one specific characterization of M matrices, which involves the notion of a linear complementarity problem. Okay. So, let me discuss that next. But in any case, I will give you one little, one theorem which has other characterizations for M matrices. You can take it as an exercise. For a Z matrix, the following statements are equivalent. First one is, of course, A is an invertible M matrix. Statement B is that all the principal minors of A are M matrices, invertible M matrices. All the principal minors of A are invertible M matrices. Statement C, A has an LU decomposition. A has an LU decomposition. So I will write like this: A equal to LU, where L is a lower triangular matrix, U is an upper triangular matrix. L and U will have 1 along their diagonals. I will simply say where L and U are invertible M matrices. Yeah. So any invertible M matrix has a decomposition. This is also called a decomposition, product decomposition, where each factor is an invertible M matrix. L is lower triangular, U is upper triangular. Either L or U can be taken in such a way that the diagonal entries are 1. Either L or U can be taken in such a way that the diagonal entries are 1. So any invertible M matrix can be written as a product of invertible M matrices, where the first factor is lower triangular, second factor is upper triangular. Why is this important? Again, context comes from solving linear equations. If you have Ax equal to B, and if A can be written as Lu in this manner, then Ax equal to B becomes Lux equal to B. So you can have Ux equal to Y, then this reduces to Ly equal to B. So you can use a backward substitution first to solve for Y, then use a forward substitution to solve for X. So this is called general Lu decomposition. So this is much easier than solving the original system Ax equal to B. There are 2 more equivalent conditions. Actually 3 more. There exists a diagonal matrix D with positive diagonal entries such that AD is diagonally dominant. Okay, you can't dispose this off. There exists a diagonal matrix with positive diagonal entries such that AD is diagonally dominant. So I am going to write 2 more statements there. There exists a X positive such that Ax is positive. What is the meaning of this? X positive means that all coordinates of X are positive. So there exists X positive such that Ax is positive. Matrices that satisfy this condition are called semi-positive matrices. semi-positive matrix. So an invertible M matrix is a semi-positive matrix. Conversely, if a Z matrix is semi-positive, then it's an invertible M matrix. That is the equivalence of A and E. Okay. If a Z matrix is semi-positive, then it must be an invertible M matrix. This is condition E. See, condition E is about, it is a statement like there exists. Condition F is for every. That is, whenever AX is non-negative, X is non-negative. For every X for which this happens, this must be true. So this is a for every statement, this is a there exists statement. Okay. Now matrices that satisfy this last condition are also much studied. They are called monotone matrices. Matrix A is said to be monotone if it satisfies this condition. AX non-negative implies X non-negative. Again, there is a relevance to this, which is that you look at the system AX equal to B. If the right hand side vector B is non-negative, that is, this is a situation. See, as I told you, there is an engineering or a economic interpretation of the right hand side. That's the input of the problem. If the input is non-negative, then a matrix that satisfies this condition, for a matrix that satisfies this condition, the solution is also non-negative. Is that clear? You have AX equal to B, B is non-negative. If such a matrix satisfies condition phi, then it means that this X will also be non-negative. So again, asking for a solution to be non-negative is a practical requirement. So all these come from considerations from practical problems. A similar interpretation can be given for this. Okay, so see the proof, so all these statements are equivalent. How does a mathematician prove these equivalence? A implies B, B implies C, C implies D, D implies Z, E implies F, F implies A. That's how we do. Some of these proofs are a little involved. For instance, D implies F involves whatever we discussed earlier, hardcore numerical analysis, if I may say so. That is diagonal dominance, Jacobi iteration, etc. So I think we have had enough of it. So let me move on to other characterizations. One thing that I would like to mention here is about matrices. Let A be monotone. So I am not going to really discuss the proof of this theorem. Again, you can refer to MAHE's book. Okay, so let me make a few statements about statement F, and then how it is related to something in connection with a notion that's given in terms of the linear complementarity problem. Let A be monotone, okay, meaning that A satisfies this condition. Then A inverse exists, and all the entries of A inverse are non-negative. It does not have to be a Z matrix. It does not have to be a Z matrix. Any monotone matrix will have this property. The converse is also true. But let's see how this is. Proved. It's more or less straightforward. I hope you understand what's going on. I've just taken statement F out, and I want to conclude something about matrices that satisfy statement F. It does not have to be a Z matrix. Okay. Okay. So how do you prove this? Any clues? AX non-negative implies X non-negative. First, we need to show A inverse exists. One of the things, standard ways to prove that A inverse exists is to show that the homogeneous system Ax equal to 0 has 0 as the only solution. So, can we prove that? Take Ax equal to 0 or u, let Au equal to 0. I want to show that u is 0. A is monotone, A satisfies that implication. Yes, you should tell me. Yeah, then u is greater than or equal to 0 because of this. A into minus u. You also have A into minus u equal to 0, then by the same implication minus u is greater than or equal to 0. Now Rn plus is a solid cone, Rn plus is a pointed cone, so u is 0. So this homogeneous system has 0 as the only solution, and so A is invertible. You must show that A inverse is non-negative. How do you show that? You don't know what A inverse is, right? You don't know how it looks like. It satisfies that implication and that A inverse exists. So how do you show A inverse is non-negative? You want to show that a matrix is non-negative, then you show that each column of that matrix is non-negative. Yeah. So consider A inverse EI. Let's call this as UI. Then tell me the next step. I'll write like this: 0 less than or equal to EI, that is AUI. Again, A of something is non-negative means that something must be non-negative. So this A inverse UI. So what we have shown is that A inverse EI is non-negative for all I. EI is this, by the way, EI is the standard basis, standard notation. So we have shown that, by the way, again A inverse EI is what? It is the ith column of A inverse. A inverse EI is the ith column of A inverse. So we have shown that all the columns of A inverse are non-negative, and so A inverse is non-negative. No Z property. The converse also holds. Conversely, let A inverse be non-negative. That is, I have assumed that A inverse exists and that A inverse is non-negative. Then A is monotone. I want to show that this implication holds. So, can you suggest how that is done? Again, one line. Let Ax be non-negative. I'll call that as Y. Then multiply by A inverse. 0 less than or equal to A inverse Y. Because Y is non-negative, A inverse Y must be non-negative, that's what this is, but this is X. And so I have shown that Ax non-negative implies X non-negative, so A is monotone. Okay, so this is really straightforward. But remember that A inverse exists and A inverse non-negative is something that we had assumed for an invertible M matrix. Okay, so I want to move on then to a characterization of an M matrix in terms of matrices satisfying a property with respect to an optimization problem, a linear complementarity problem. I believe Professor Niyogi is coming next week, so he will discuss this notion of linear complementarity problem in a much greater detail. I am going to only scratch the surface. That is, the plan is to link monotone matrices to a property coming from the linear complementarity problem. Okay, that's the idea. Which in turn gives a relationship between M matrices and this property coming from LCP. Okay. Okay, so this is what we have. This time I'll restrict my attention to real square matrices. You are given a matrix and a specific vector Q. The linear complementarity problem defined in terms of these two parameters, LCP A comma Q, is to find a vector X that satisfies the following conditions. Non-negative, X is non-negative. Define a vector Y as AX plus Q. You require this also to be non-negative, and that the dot product between these two vectors is 0, and X transpose Y equals 0. This is a linear complementarity problem. Okay, so note that A and Q figure here. The problem is called linear because this matrix A, because of this matrix A. If you replace that by a nonlinear function, then it's a nonlinear complementarity problem. What is complementarity here? Complementarity is really this equation. Remember, X and Y are non-negative. Of course, if you have studied undergone a first course in linear programming, you know what it is. This condition tells you that X transpose Y equal to 0 means that summation Xi, this is the usual inner product, no? Summation Xi Yi is 0. Now look at each Xi Yi, so Xi is non-negative, Yi is non-negative. So summation Xi Yi non-negative equal to 0 means that each term must be 0, which means that Xi Yi is 0 for all I. If Xi is positive, then that corresponding Yi must be 0. If Yi is positive, then the corresponding Xi must be 0. That is complementarity. If one is present, the other one is not present. That's complementarity. So this is really the complementarity condition. These are feasible conditions. Now this is a difficult problem, hard problem to solve. Even if you are for a specific Q that's given, this is a hard problem to solve. Under some assumptions on A. For example, if A is a positive symmetric positive definite matrix, then this can be converted into a convex programming problem. That is, this can be converted into an equivalent quadratic programming problem, which in turn can be solved even by simplex method. If A is symmetric positive definite, Wolf's method, just a little variant of the simplex method. But in general, this is a difficult problem to solve. Now there are classes of matrices A for which this problem has been attempted. How to solve this problem? When A belongs to a certain class. Okay. But before that, if you want, can I give an example? Let's take A as 1 1 1 1. Let's say I'm giving you the vector Q as 1 0. Can you give me a solution for this Q? I want X non-negative, AX plus Q non-negative, X transpose Y equal to 0. 0 is a solution. X equal to 0 is a solution. Does it have another solution? 0, 1 is also a solution. X equal to 0, 0 is a solution. X equal to 0, 1 it goes the other way around, that's a solution, etc. A linear combination of these two, okay, that is nothing, just a multiple of this. Any non-negative multiple of this, that's also a solution. Okay, so this problem has infinitely many solutions for this choice of A and this Q. What about the same A, I change Q to be 1 minus 1? Hmm? 1 1 is a solution. About 1 1, I don't know. See, ax plus q needs to be non-negative, and that yeah. So 1 1 is not, doesn't look like a solution. Okay. See, it's not a guessing game. It's a difficult problem. It's a difficult problem to determine if this problem has a solution given a particular q for a given matrix A. But I can tell you this much. For this A, you take any Q, this problem has a solution. That comes from a theorem. So I'll write it as a fact which can be verified later. For the above A, for any Q, LCP A comma Q has a solution. Now this is a sweeping statement. For any Q, this problem has a solution for this A. Now, so in order, if you make a sweeping statement, then something strong must be in the background. That is Karamadian theorem. I just stated this a little while ago. I'll come to that a little later. Now, there are classes then, matrix classes classified according to what one expects from the linear complementarity problem. So I'll give you two classes. By the way, I'm not asking a unique solution. In this particular case, there are at least two solutions, right? First definition, matrix A is called a P matrix if all its principal minors are positive. If all the principal minors of the matrix A are positive. You know what a principal minor is, right? Matrix A is called a P matrix if all its principal minors are positive. So what is a principal minor if you have any questions? For this A it will not happen. Yeah. No. It will not be always a solution.
If you find one solution, then pass it to non-negative scalar multiple.
Not necessary. Not necessary. This Q imposes a restriction. It has happened in this case that non-negative multiple is a solution, but otherwise there is no guarantee. Q can have a negative coordinate, and so that can come in the way of this sum to be non-negative. So it's not always true. Yeah, that's a P matrix. So all principal minors are positive. So what is the meaning of what is a principal minor? You know what it is, then I'll move on. So then let me give an example of a P matrix. I've just randomly written a matrix and I'm claiming that this is a P matrix, but you can verify that principal minors are positive. Is that okay? So first of all, what are the principal minors? Delete the first row, first column, 24 minus 6. Then delete the second row, second column, 18 minus 3. Delete the third row, third column, 12 minus 2. So all those are positive. Diagonal entries are of course principal minors. They are all positive. I leave it for you to verify that the determinant is positive. So this is a P matrix. But when I wrote this down, I had something in the back of the mind. Yeah, it's an invertible M matrix. So I used one of the characterizations. See, I wrote down a Z matrix carelessly, and then of course the diagonal entries must be non-negative because the principal minors must be positive. But I wrote this down then with only one care, which is that the row sums are positive. So this is a matrix which satisfies, this is a Z matrix. There exists X positive such that AX positive, that is E, all entries 1. E positive such that AE is positive. So from that theorem, I know that this is an invertible M matrix. I know that every invertible M matrix is a P matrix. So I really used something which I didn't reveal. Now, of course, proving those things I will not do today. Quite a bit of an effort, and that's not the intention also. So this is an example of a P matrix, okay? So one class is given by invertible M matrices. This is chosen in that manner. What is not a P matrix is there. This is not a P matrix. Obvious, determinant is 0. Okay. So what is this thing coming up when we are discussing LCP? This is a theorem. For a reference, I will ask you to look at either Berman-Clemens or Kotelpang and Stone. Kotelpang and Stone have written a book by titled Linear Complementarity Problem. Berman-Clemens is, of course, is non-negative matrices in the mathematical sciences. So what does this theorem state? This states that A is a P matrix if and only if LCP A comma Q has a unique solution for all Q. Now you see, I mean, this is quite surprising. There is something that you are asking on the principal submatrices of the matrix A, but it has some connection to an optimization problem, connection to LCP. So I just wanted to state this result because it may take about an hour to prove this. This is one class. So P matrix is one class. I don't know why the name P came about. See, this name was given by there is a famous paper by Fiedler and Tack. Miroslav Fiedler and Tack is PTAK. They wrote this paper in 1964. This appeared in the Czech Mathematical Journal. And I have only one suspicion that probably it was this guy who gave this notion. But I have no other evidence. Okay, that's a P matrix. By the way, this paper, if you go to MathSciNet, look at the citations, there are some 170, 175 citations for a paper. Berman-Clemens again have something like that, a proportion. Again, this book is also widely referred to. Okay, this is one class. There is another class. A is called a Q matrix. Okay, now this is not really a definition. It's called a Q matrix if LCP A comma Q has a solution. See, here it is unique. Has a solution for all Q in Rn. You don't ask for a unique solution. But what kind of definitions is it? It's difficult. There is a unique X. No, solution is this X. And so there is a unique X for which these constraints are satisfied. See, there is, with LCP we don't associate an optimal solution, etc. But in some cases it can be modeled as an optimization problem. Now, unique solution means that unique X for which those constraints are satisfied. That's all. Okay, now this is quite complicated. How do you verify that LCP A comma Q has a solution for all Q? It goes without saying that P implies Q. So I am using the same symbols here. P for P matrix, Q for a Q matrix. So P implies Q is obvious from this theorem. This is not even a good statement. Now Q does not imply P. Q does not imply P. But how in the first place will you verify that something is a Q matrix? It goes by this definition. How do you verify that something is a Q matrix? One of the most frequently used results to check that a matrix is a Q matrix is due to Karamardian, and it's called Karamardian theorem. Now, Karamardian visited this problem twice. I'll just give you one reference. 1976 Jota. And he used fixed point theory arguments to prove this theorem. He considered a very general complementarity problem. I am only looking at a diluted version of that statement. From Karamardian theorem, for instance, it will follow that this is a Q matrix. Okay, we'll verify that. So, what is Karamardian's theorem? If LCP A comma 0 and LCP A comma Q for some Q positive have 0 as the only solution. Have 0 as the only solution, then LCP A comma Q has a solution for all Q. This is Karamardian theorem. Now, this is an existential theorem. This doesn't give a construction. That is, it doesn't tell you for which Q this will work. How to find that Q? You don't know that. But before that, observe, look at LCP A comma 0. Something similar to this vector Q. See, this Q is a non-negative vector, right? This Q is a non-negative vector. So, if you go back here and take X to be 0, then that is trivially a solution. So, we can write this immediately. If Q is a non-negative vector, then X could be taken to be 0. In particular, if Q is 0, then X could be taken to be 0. Okay. So, if you go back to these two problems, LCP A comma 0, LCP A comma 0 has 0 as a solution. LCP A comma Q, when Q is positive, also has 0 as a solution. But you want 0 to be the only solutions. So, this is the requirement really. These two problems of course have 0 as a solution, but this theorem, the sufficient condition is that these two have 0 as the only solution for some q positive. See, we don't know what that q is. For some q positive, if this happens, then LCP A comma q has a solution for all q, that is A is a q matrix. Let me write that here. No. See, these are two individual problems. Both have 0 as a solution. Each problem has 0 as a solution. The requirement is that they must have 0 as the only solution. There is no other solution. There is no commonality. Yeah. No. LCP A0, you can verify here also. LCP A0 for this, you can verify. Okay. For this problem, 0 is the only solution. But in general, it's not. Isn't it? I hope it's clear. See, if Q is non-negative, then 0 is a solution. That need not be the only solution. In fact, we have that here. If that happens for some Q positive and the homogeneous problem, this is called the homogeneous problem. Homogeneous problem also has 0 as the only solution. That is, so you write this down and see what it says. Yeah. No, this one, it is not. In fact, I want to use this theorem to show that this is a Q matrix. In this problem, for this problem, the homogeneous problem has 0 as the only solution. Yes, that's right. To begin with, the homogeneous problem must have 0 as the only solution. That happens here. Okay, so let's verify the statement for this matrix, and that was the reason why I wrote this down and claimed that it is a Q matrix. Yeah, there is something I wanted to say here. Karamadian did not use the term Q, so we need to write this again. That is, A is a Q matrix. Okay, now for understanding, you write down the problems LCP A comma 0. What is this problem? X non-negative, AX non-negative. Oh, thanks. This is no biscuits. This is too much. No. Thanks. I don't know how many of you are teachers here. 3 hours with a 20-minute break is not easy. And if you are the only person talking. I missed my coffee in the morning. That's not a complaint. Yeah, can you try to prove this? Can you try to prove that this matrix satisfies the theorem, so it's a Q matrix? Two by two is only simplicity. Any n by n, all entries 1 will have this. LCP A0 is X non-negative, AX non-negative, X transpose A is equal to 0. we want to show that x equal to 0. These three conditions imply that x is 0. So if you go back to this problem, you are requiring x to be non-negative. Ax non-negative means, okay, that is trivially satisfied. x1 plus x2, x1 plus x2. That is non-negative. Look at this condition. 0 equal to x transpose ax. I will find it easier to use the inner product. I need this later also. Yeah, oh, this is just a quadratic form. Okay. x1 square plus x2 square plus 2x1 x2. Now this is x1 plus x2 the whole square, that is 0, means that x1 plus x2 equal to 0. x1 is equal to minus x2, but along with this tells you that x is 0. Okay. A similar calculation for LCP A comma E is 1 comma 1. I leave this for you, a similar argument. For this is a positive vector. This is a positive vector. So the homogeneous problem has 0 as the only solution. This problem for a positive E, for a positive vector, has 0 as the only solution. So this matrix is a Q matrix by Carmardian theorem. Okay. But remember, if it is, if you try several vectors Q positive for which for which you are trying to test if this problem has a solution, you don't know how many Qs you can take. So there is only a sufficient condition. It's not a finite algorithm, right? You may take any number of Q positive for which there may be more than one solution. You don't know whether for the next Q it will turn out to be only one solution. So you can't really apply that in practice. Okay, what is the connection then? So what is the connection? Right? P implies Q. Q does not imply P, but there is a nice theorem. Again, I can only state that without proving. There is a nice theorem which states that if it's a Z matrix, then these two notions coincide. Let A be a Z matrix, then A is in P if and only if A is in Q. P implies Q is always true for whatever matrix class you start with, but Q does not imply P, but for Z matrices these two are equivalent. What I want then is, so there is something that we discussed earlier coming in, which is Z. What I want to do is now look at Q and that monotone criterion. Okay, I'll show that those two are equivalent. Okay, Q and monotonicity criterion are equivalent. So that's a theorem that I want to prove. This really gets us another characterization of an invertible M matrix. I'll give that statement a little later. What is this result? Let A be a Z matrix. Then A is in Q if and only if A is monotone. Now this is something you might not find in any textbook. So let's look at the proof. Okay, I want to show that if A is Q, then A is monotone. Let A belong to Z and Q. we want to show A is monotone. Okay, that is, we must show that. Remember what monotonicity is. We must show that Ax non-negative implies X non-negative. First, I want to show that A is invertible. Okay. Let little q be positive. I have that A is a Q matrix, so there exists X non-negative such that y equal to, I am writing Ax minus Q, that is non-negative. I am not writing Ax plus Q, I am writing Ax minus Q, because if it's a Q matrix, it doesn't matter. Q belongs to Rn, that's all. Together with, I'll use this inner product, again, this is convenient. Together with this complementarity condition. Okay, now we need to use Z property, which see, what is Z property? Z property is that the off diagonal entries are non-positive. Okay, there is a different way of writing it which allows us to go to even an inner product space. What is Z property? Aij non-positive. What is Aij? Aij is the inner product of Aej Ei. This is really Aij with a standard inner product. This is less than or equal to 0. Now what do you know about Ei and Ej? They are non-negative, right? Ei, Ej are non-negative, and okay, see, what is this is when I is not equal to j. Okay, so they are non-negative and that the dot product is 0 because I is not equal to j. This is really Z property. I have now rewritten it, which allows us to write in any cone. You know what a cone is. You can take a cone, you can take its dual cone, and then you can define this. That is, I'll go to a very sweeping statement. I am saying that A is Z if and only if A satisfies X non-negative, Y non-negative, XY equal to 0, imply AXY is less than or equal to 0. A is Z if and only if this thing holds. I'll leave it for you to verify this. I've just illustrated for the standard cone. For the standard basis. I've illustrated this for the standard basis, but this is something that's true. You can write out X and Y in terms of the standard basis. X is summation Xi Ei, where each Xi is non-negative. Y is summation Yi Ei, each Ya non-negative. Dot product 0. Expand this out. This is X transpose A transpose Y. Expand this out, you will see that this is less than or equal to 0. And you can go the other way around. If A satisfies this, then by employing the standard basis, it follows that A is a Z matrix. Now this is something that allows us to go to a general cone, its dual. One can talk about a Z operator on a cone. Okay. Lorentz cone is something that's immediately applicable. That's what I'm going to use here. I have Ax minus Q non-negative. I have this condition, right? I have that condition. X and Y are non-negative. So I must have Axy to be non-positive. This condition. Axy is non-positive. So I must have this. Write this out and see what you get. Ax is Y plus Q. and this is y. So this is norm y square plus inner product q with y. This is a non-negative number. Look at qy. Q is positive to begin with. Y is also non-negative, so this is strictly positive. Sum of two non-negative that's less than or equal to 0 is possible only if each is 0. In particular, y is 0. That is, there exists x non-negative such that ax equals q. Y is 0 for all q positive. Is it okay? For every q positive, there exists x non-negative. We have shown that this y must be 0, so ax equal to u is satisfied. Ax equal to q is satisfied. From this, invertibility of A follows. How? A is? From this, invertibility follows. Monotonicity will also follow. I'll come to that. But Q is positive. We have shown that. See, there are different ways of arguing. See, Rn plus is a generating cone. You know what a generating cone is, right? You know something about cones, isn't it? No. Rn plus is a generating cone. So this equation tells us that you take any vector, in Rn, call that W, then such vector can be written as difference of two positive vectors. In fact, Rn is interior Rn plus minus interior Rn plus, generating cone. And so it's an onto map. That's one way of arguing. Onto map, square matrix or rank nullity dimension theorem, invertible. Another way is Q is positive, so interior Rn plus is contained in the range of A. I have a subspace which has interior, so it can't be a proper subspace. It must be the whole space. So A is invertible. So either way you get this conclusion that A is invertible. Okay, a subspace in general, even in infinite dimensions, it's true. Interior is contained in a subspace if and only if the subspace is the whole space. And so again, a little bit of a real analytic argument that comes here. You can either use that or rank nullity dimension theorem. But again, for rank nullity dimension theorem, in order to use that, you must observe that Rn plus is interior Rn plus minus interior Rn plus. Interior Rn plus is a generating cone or a reproducing cone. So A is invertible, right? This shows that A is invertible. This, the proof actually stops here. This also shows that A inverse is non-negative. Can you tell me how? This proof also shows that A inverse is non-negative. Using invertibility of A. Multiply both sides with A inverse, yes. Yeah, so A inverse Q is non-negative, that's all. 3 multiplied by A inverse, it tells us that X is equal to A inverse Q. Now A inverse Q has to be strictly positive, in fact, because A has no 0 rows, it's invertible. So X equal to A inverse Q, and so A inverse is non-negative, okay. The only problem there is you are saying X is not, there exists X non-negative, but if you look at, let Q be non-negative, there exists X non-negative such that AX equals Q, but A is invertible, so X equal to, oh okay, it's the same thing maybe. That is X non-negative. So we have shown that for every Q non-negative, A inverse Q is non-negative. For every Q non-negative, A inverse Q is same thing here. Only thing is strictly positive. So A inverse is greater than or equal to 0, but we have seen earlier that this is the same as showing that A is monotone. Okay, AX non-negative implies X non-negative. So what we have shown is that if A is a Z matrix, which is also a Q matrix, then it must be invertible, and that the inverse is non-negative. In particular, it is monotone. Does it take us back to invertible M matrix? A is a Z matrix, A inverse is non-negative, so A is an invertible M matrix. So if A is a Z matrix which is also a Q matrix, then A is an invertible M matrix. I am going to leave the converse for you to show. For the converse, use Karamadian's theorem. You want to show that a certain matrix is a Q matrix. Karamadian's theorem is one frequently used result. So converse, I am leaving it for you to verify. It's again not difficult. Just Karamadian's theorem. Converse is an exercise. Hint: Karamadian theorem. Together with this result, then we have the following corollary. It's just putting things together. Let A be a Z matrix, then A is an invertible M matrix. If and only if A is a Q matrix. I have established this through the monotonicity criterion F. And remember that for a Z matrix, Q criterion coincides with the P criterion, so that's another equivalent statement. So, along with the 5 equivalent statements that I had given, in particular, A is a semi-positive matrix, A is a monotone matrix. You can include these two. A must be a P matrix, A is a Q matrix. So, these are 2 more equivalent statements for a Z matrix to be an invertible M matrix. Okay, and this was the reason why I took that particular invertible M matrix. I took a Z matrix with the property that AE is positive. So the semi-positivity condition is satisfied, and so it must be a P matrix. Okay, so I'm quite sure there are about four lectures by Professor Niyogi. Some of these results will be proved by him. My context was different, so while I proved a few things, I'm skipping a few others. So this is about invertible M matrices. There is something that we have done a while ago, generalizing these to singular matrices. I want to discuss that next. But before that, if you have any questions, I'll be happy to answer. So I need the notion of the Moore-Penrose inverse, group inverse. I'll recall those things. And then give a result which resembles those 5 statements, something like that. Remember, there are at least 50 equivalent conditions for a matrix to be an invertible M matrix. So I'm just looking at one particular portion and I was working on it. I am working on it. Invertible M matrices, there have been generalizations to the space of symmetric matrices. The context comes from semi-definite linear complementarity problem. Lyapunov operator, asymptotic stability of dynamical systems. So again, lot of physical relevance, practical problems which are solved by using Lyapunov operator, where this SDLCP, semi-definite linear complementarity problem comes. Okay. Okay. So let's then go to the notion of generalized inverses. So I first look at the concept of the Moore-Penrose inverse, then the group inverse, and then one little theorem, which will look like this invertible M-matrix statement. Okay, so what is a Moore-Penrose inverse? Traditionally, Moore-Penrose inverse has been defined in the following manner. By the way, Moore was a 20th century, even 19th century mathematician. Penrose is very much alive. He is a physicist. He is in the Cambridge University. Moore wrote something towards the end of the 19th century, and because of the obscure notation, people didn't understand what his paper contained, and because of which he didn't get the recognition. It was Penrose who, about 60 years later, who wrote down these equations again, sharpened and proved uniqueness. And see, he wrote two papers which appeared in the Proceedings of the Cambridge Philosophical Society. He showed how these two papers, how applications could be handled, and then it was just, it became famous because of what he did. But since this idea was conceived earlier by Moore, the name Moore is attached along with this. Now, what exactly is this Moore-Penrose inverse? You start with an M cross N matrix with complex elements. Looking at a general setup, we ask for a consideration. Consider these equations Ax. So I am asking x to be in C n cross M. So the order is the other way around. Do these equations have a solution? That's the question. Axa equal to A, Xax equal to X, Ax star equals Ax, Xa star equal to Xa. Of course, Manjunath students will be knowing a lot of these. So look at the symmetry between the first two and the last two. If there exists an x that satisfies all these four equations, such an x is called, such an x can be shown to be unique first, and that it is called the Moore-Penrose inverse of A. Quickly, a simple proof of uniqueness. Shall we do that? It's afternoon, close to lunchtime. So how do you prove uniqueness? Uniqueness is proved if starting with the two solutions. Let's say x and y are two solutions. Show that x is equal to y, right? That will prove uniqueness, but there is a more basic question of existence. I will come to that. So let's say there are two solutions, then this is how you do. X is equal to xax. It is x into ax, which can be written as xax star. I'll keep this x as it is. Write this as x star a star. X into, keep x star. For a star, go to the first equation of y, for y. So that's a star, y star, a star. And then bring in this xx star, a star, y star, a star. One needs to do this carefully. X into x star a star is ax whole star is ax. Similarly, this is ay whole star, that is ay. Again, axa is a, so this is xay. This is one half of the proof. From this, you write xa whole star y. And then this is a star x star. For y, you write ya into y. This is a star x star ya star y. This is a star x star. I'm just hoping that I'll get y on the right hand side. A star y. Yeah, so combine these two. A star y, ya whole star, ya star is ya y, that's all. Okay. So x equals to. If you are not careful, you will be caught in a loop. But remember that you can't get uniqueness if you don't use all the 8 equations. So what is the meaning of that? The meaning is that even if you drop any of these equations, you won't get uniqueness of a solution. So this is uniqueness if assuming that the solution exists. The solution exists can be proved in several methods. One is full rank factorization. The other one is reducing A to a householder Smith normal form, etc. I want to look at one more method of showing existence, that is by the singular value decomposition. So are you aware of SVD? So let me straight away use that. This is called the singular value decomposition. Any complex rectangular matrix A can be written in this manner: U sigma V star, where U, C, M cross M and V, C, N cross N are unitary matrices. U star U equal to UU star equal to identity. Similarly for V, sigma is a block diagonal matrix. First block is D, all other entries are 0, block zeros. It's possible that this column block does not appear. It's possible that this 0 row does not appear. That will depend on the rank of the matrix A. If you take rank of A equal to R, then this D is R cross R. D is a diagonal matrix with diagonal entries denoted by sigma 1, sigma 2, etc., sigma R, where these numbers are arranged in such a way, so you can arrange the columns of U and V in such a way that these numbers satisfy sigma 1 greater than or equal to sigma 2, etc., greater than or equal to sigma R, which is strictly positive. R is the rank of the matrix A. Note that this positive thing comes from the fact that A star A or A star, the number of non-zero eigenvalues of A star A or A star is equal to R. Because A star A or A star is positive semi-definite, these numbers are non-negative. But because the rank is R, each of these will be positive. And you can order them because it's a Hermitian matrix. That is, the squares of these numbers are the eigenvalues of A star A or A star, doesn't matter. Non-zero eigenvalues will be the same. The rest of the eigenvalues may be padded by zeros. So the squares of these numbers are the eigenvalues of A star. This is the singular value decomposition. Nice theoretical tool, but observe that it involves singular values which are square roots of eigenvalues, which are difficult to find. Okay, so if you have to compute these, then it's a hard problem, but if you have the information with you, then it's very good to use in many situations, because this gives a very stable method of finding the Moore-Penrose inverse. So what is the thing then? Moore-Penrose inverse, let me simply state this. If A has this singular value representation, then the Moore-Penrose inverse is V sigma dagger U star. This is the V sigma dagger. This is the formula for the Moore-Penrose inverse. All that I need to do is tell you what sigma dagger is. Sigma dagger will be D inverse, right? All entries are positive, so it is D inverse, and then I must write 0 transpose, 0 transpose, 0 transpose, because it's not the same as this 0. See, this 0 may be a rectangular 0, whereas even this is a rectangular 0, no? Yeah, so you need to take the transpose and then do this. So I am claiming what is, I have written some notation also without explaining what it is. A dagger satisfies the Penrose equations. So this is the Moore-Penrose inverse. Not so. A dagger is called the Moore-Penrose inverse. I leave it to you for verifying that this formula, if this is what A is, this satisfies those 4 equations. You will have to use the unitarity of U and V and then sigma sigma dagger. Sigma sigma dagger will be identity, all other blocks are 0, and that will help in simplifying the calculations. Now this is called a generalized inverse or a pseudo inverse. Pseudo means false. So not actually the inverse, but the pseudo inverse. Remember that when A is square and invertible, then the inverse trivially satisfies these equations, and so the Moore-Penrose inverse coincides with the usual inverse. So this reduces to the usual inverse when the usual inverse exists, and this is more general because this looks like the usual inverse. But remember that there was a choice that we made, a choice of 4 equations. Why these 4 equations, and why did people stick to these 4 equations? There is a lot of nice theoretical, there are a lot of theoretical properties for considering the 4 equations. Maybe I'll just illustrate one, and that's the reason why these 4 equations are used. But if you are a student of statistics, you will know that it's enough if you consider equation 1 and 3 in many practical problems. Linear unbiased estimator, sometimes 1, 2 and 4 will be enough to consider. So there are some least square solutions. If you want the least square solution, the least norm, then you have to consider all the 4. If you are interested only in linear equations, then equation 1 is enough, etc. So this depends on what the context is, what problem you are working at. But this is stood the test of time. This is called the Moore-Penrose inverse. Okay. If you want some quick examples, let's take A to be 1 0 1 0 1 0. See, here the columns are linearly independent, and so A star A A transpose A is invertible. Some linear algebra quickly. Columns are linearly independent. So null space of A is singleton 0. Look at A transpose A. It's a square matrix, it's invertible, and one can compute that the Moore-Penrose inverse is A transpose A inverse A transpose. If I am right in this example, it will turn out to be A, but just check. Not very sure. A transpose. Just check this particular part. I'm not sure. It looks like, but so there is a formula that involves a usual inverse. If A has 1 1 1 2 1 0, the rows are linearly independent, then you can verify that the Moore-Penrose inverse is A. What is the? It's a right inverse. A transpose inverse A transpose. It's a right inverse, and so I have given formulas which don't depend on the singular value decomposition, because for 2 by 2, 3 by 3, don't use singular value decomposition. So I am just asking you to verify these. No, it's not A terms. Okay. So I thought the inverse is identity. So okay. Finally, what is the Moore-Penrose inverse of this matrix? All entries 1. Let's say this is M cross N. Do you remember? Oh, I see. Okay. Yeah. Okay. So what's the Moore-Penrose inverse of this? That's what you have. Okay. So here are some simple examples to verify. Okay. So as I told you, all the four have a nice property, which is the following. See, consider the system Ax equal to B. Again, Ax equal to B. Linear algebra is just this equation, Ax equal to B. Now there are problems where this will not have a solution. For instance, when you do, see, there are many empirical formulas. You will have one empirical formula like this: L is equal to x1 W plus x2. Now W is a weight, L is a length or the displacement. That is, you have a spring and you attach a mass to the spring. There is a certain coefficient of spring that you want to calculate. Why? Several springs make up a bridge or a column, for example. So you need to know some of those numbers rather accurately. So you have a spring, you are attaching a weight. You need to consider the coefficient of that spring, the weight and the length, length of displacement. They are related by this formula. This is an affine formula. This is this is actually Hooke's law. Okay. But Hooke's law informally says stretch by strain equal to constant. But there is one more thing that appears here. It's not a constant. This is an affine relationship. So how does one determine? The unknowns are x1 and x2. Xi are the unknowns. How does one determine x1 and x2? One performs experiments in the lab. There are two unknowns, but we do more experiments than the number of unknowns that are required. We need just two, but we do at least three or more. Now this is done in many practical problems, statistical applications, even this opinion poll, etc. Exit polls. There is a lot of least squares thing coming. You do more experiments than that are required. So, and then tabulate, something like this. You will have something like this. This is L, this is W, and this is L, for instance. 1, 2, 3. This is W, this is L. I'll have, let's say, 2, 4, and a 5.5. Some hypothetical data. Now you substitute this into that formula, you will not get a solution. There is no solution for this system. Okay. This whole thing can be written as, so for this data, A is 1, this will go with so this is the problem. This is a problem Ax equal to B for this experiment. You can verify that this does not have a solution. Yeah, first two equations have one solution, whereas the last two, the second set of two equations, have a different solution. So they are inconsistent. But you can't delete any of the equation. You can't modify the, you can't fudge the data. You have to solve this equation. This equation does not have a solution, but you have to solve it. So what one does is to look at minimize LE square solution. Ax equal to B has no solution. So one minimizes norm Ax minus B. What is used is a 2 norm. Why 2 norm? 2 norm is closely related to the adjoint operator star. And the function, the statement I made earlier, the function that takes a vector to the 2 norm is a differentiable function. So one can take the derivative of this to 0. When you take the derivative of this to 0, you will get the equation A transpose Ax equals A transpose B. Now numerical analysis discusses this equation quite frequently. These are called normal equations. This is the stationary equation of this functional. F of x equals norm Ax minus B, f prime x equal to 0 gives you this. That's the stationary point. So you need to solve this, this equation. This is always consistent. So something like magic. This equation is not consistent. You pre-multiply by A transpose, this will always become consistent, but it may have more than one solution. That will depend on the rank of the matrix A. If the columns of A are linearly independent like this, then this will have only one solution. Otherwise, this will have infinitely many solutions. Again, this is a practical problem. I can't deal with infinitely many solutions. I want a unique solution. That unique solution is given by A dagger B. This is a summary of the Moore-Penrose inverse. That is, if A is square invertible, then x equal to A inverse B is the only solution. You take it or leave it, that's the only thing. A is rectangular, it has infinitely many solutions. Then you will have to choose the one that's closest to the origin, minimum norm solution, that's given by this. Ax equal to B has a unique, it's a rectangular system, it has a unique solution, that's given by this. Ax equal to B does not have a solution, but the normal equations have a unique solution, that is given by this. Ax equal to B does not have a solution, A transpose Ax equal to B has infinitely many solutions, then the one with the least norm, the one that's closest to the origin, is again given by x equal to A dagger B. So this kind of summarizes the entire situation for the system Ax equal to B, consistent, inconsistent. And so it's important to use this Moore-Penrose inverse. But there are problems with this normal equation. This is a numerically unstable equation. This is what is called as an ill-conditioned problem. The condition number is large, and so if the initial data B has some errors, the errors are blown up when you solve this equation. So this has complications, okay, but in principle all these things work nicely. This is an important summary for the Moore-Penrose inverse, okay. Any questions? There is another inverse called the group inverse. So for the group inverse, Moore-Penrose inverse comes from 4 equations which are symmetric and time tested, reasons as to why they are considered. For the group inverse, one considers only a square matrix because so you take the first 2 equations from the Penrose equations, and along with this you ask x to commute with A. It's because of this requirement that you need you can talk about the group inverse of a square matrix. Now these equations, when a solution exists, it is unique. When a solution X exists, it is unique. I am not going to prove it, but they may not have a solution. The Moore-Penrose inverse always exists. It comes from the singular value decomposition. You can see it's always there, but the group inverse may not exist. A solution may not exist. Now the group inverse will be denoted by a hash. Okay. Moore-Penrose inverse is A dagger, this is A hash. For an example of a matrix which does not have the group inverse, someone? Something with index 2. Can you give an example? 2 by 2, 3 by 3. Group inverse does not exist. All entries 1 will have group inverse. It's a symmetric matrix. Symmetric matrices. 1101 invertible. Okay. 0100 nilpotent. Yeah. This will not have group inverse. This will not have group inverse. You can verify the 4 equations, 3 equations. At the moment, that's what you have. But for the group inverse, so what is this? A hash is called the group inverse. A hash is called the group inverse. It may not exist, but if it exists, it's unique. Okay. What is the characterization? There are several. A hash exists if and only if rank of A is rank of A square. It exists if and only if range of A and null space of A are complementary. Etc. Okay. Range of A and null space of A are complementary subspaces. An example of a matrix which has group inverse, all entries 1, square, all entries 1. Here the Moore-Penrose inverse is equal to the group inverse because it's a symmetric matrix. So it's 1 by n square A. Now remember, group inverse does not have the adjoint operation in its definition, so it's useless for least square solutions. Okay, but it's useful in some other applications. I will not get into the details, but one application is in solving differential equations, where a more general notion called the Drazen inverse is used. Okay, I will not get into that. See, this is another generalized inverse, because if A is square and invertible, then these equations are trivially satisfied. So this is another generalized inverse, distinctly different from the more Penrose inverse, not just in the equations but in the applications as well. So there are some dynamic differential equations which can be, wherein you can apply the group inverse. There is a more important application which is again done by MAHE in finite Markov chains. So in Markov chains, there is a transition probability matrix. A matrix is called transition probability matrix if the entries are non-negative, either the row sum is 1 or the column sum is 1. So if A is I minus T, where T is a Markov matrix or a transition probability matrix, then the group inverse of A hash exists. Group inverse of A hash exists, and that it's not just the existence of the group inverse. The process of the Markov chain can be described in terms of the group inverse. Okay, this is a 30-page article written by MAHE. It appeared in Siam Review, if I am right. Now note that T is a non-negative matrix whose either whose column sums is 1 or whose row sums is 1. So you can apply Perron-Frobenius theorem. So the spectral radius of T is 1. How many times it appears? Multiplicity we don't know, but spectral radius is 1, and that's the number here. So this is now like an M matrix. This is like an M matrix. Invertible M matrix. This is a singular M matrix, that's an invertible M matrix. Spectral radius of T is 1. Yeah. Spectral radius of T is 1. For the invertible M matrix, you want R to be greater than spectral radius of B. B is non-negative, here T is non-negative. Spectral radius of B there is less than R. Spectral radius of T is precisely R. R is 1. So this is a singular. This is called a singular M matrix. If T is an irreducible Markov chain, if T is an irreducible matrix, then this is an irreducible singular M matrix. Irreducible singular M matrices are studied. They have some nice properties that are similar to the invertible M matrix case. Okay. So I am going to write down a result which will look like several equivalent statements that I wrote down for an invertible M matrix. Okay, but just like an invertible M matrix, there is a notion which see, if you just look at singular M matrices, it's complicated. There is a via media which is to look at what are called as M matrices with property C. So let me describe that. M matrices with property C. Property C. Now this was defined by Plemons. This was defined by Plemons. I don't know why the C came. I have absolutely no idea. Plemons is P. This is M matrices with property C. So what are M matrices with property C? A equal to, let's write Ri minus B. B is non-negative. R is equal to spectral radius of B, and B by R is convergent. is semi-convergent. The word is semi-convergent. This is the definition. So I want you to look at how this is related to the invertible M matrix case. If it's an invertible M matrix, you can write it as Ri minus B, where R is strictly greater than the spectral radius of B. B is of course non-negative. Now, if R is strictly greater than spectral radius of B, then B by S converges to 0. Here we are not asking B by S to converge to 0. B by R, we are asking that to converge to a possibly constant matrix. The constant matrix may not be 0. This is called semi-convergent. Convergent is this converges to 0, which happens for an invertible M matrix. Okay, so this is a class. This is a class of matrices which is not too bad as singular M matrices, not as good as invertible M matrices, something that lies in between. Why was this thought of? Again, because of applications. It's related to something like this. Okay, so what about an example of an M matrix with property C? Look at this matrix. 1 minus 1 minus 1 1. This is an example of an M matrix with property C. I'll also give you the reason as to why it is the case. You can write this as 1 0 0 1 minus 0 1 1 0. Okay, this is identity minus B. B is non-negative and lambda square minus 1 equals 0. 1 is an spectral radius of this is 1. So this is a singular M matrix, I minus B. I need to verify that B by 1 is convergent, semi-convergent. I need to verify that B by 1 is semi-convergent. So how will you do that in this case? See, this is a symmetric matrix, and so you can do the apply spectral theorem. Write this B as U D U transpose. D is a diagonal matrix minus 1 1. Okay, so this will not work. This will not work. Okay, then 2 0 0 2 1 1 1 1. Yeah, this representation will work. 2 times identity. The spectral 2 is an eigenvalue. 2 and 0 are the eigenvalues. So this is a singular matrix. Now this is a symmetric matrix. You can the power is convergent. Okay. B power k converges to a matrix C, constant matrix C. The previous one doesn't work. Yeah. So you need to make an appropriate choice. So this is an M matrix with property C. One exercise for you. The following matrix is not an M matrix with property C. See, it is M matrix together with some condition, right? So you must first show that this is an M matrix and then show that it does not have property C. So there are M matrices which may not have property C, singular. Take this matrix 0 minus 1 0 0. Show that this is an M matrix indeed, but okay. So here, when I mean an M matrix, I mean a singular M matrix. This is a singular M matrix. This is a singular M matrix, that is, you can write it as Ri minus B, where R is equal to spectral radius of B, B non-negative, but it does not have property C. Does not have property C. Now that will be slightly difficult to prove. That may turn out to be difficult to prove in some examples, but in this example, It's the straight definition applies. There is another thing. If it's an M matrix, see if it's an invertible M matrix, then it is invertible, and the inverse is non-negative. There is a similar result. I should probably stop here. Let A be a Z matrix. Then A is an M matrix with the property C if and only if the group inverse exists, and A is an invertible M matrix if and only if A inverse is non-negative. A is an M matrix with property C, by which I mean a singular M matrix with property C, if and only if A inverse exists and A hash exists and A hash is non-negative on range of A. This is the generalization. This is just one of those. This is something that's more general than what we discussed earlier for an invertible M matrix. There are other notions like a P hash matrix, range monotonicity, etc. I'm not going to get into that. This is just one part of a general result that we proved recently. You can look at the details in linear algebra applications. Myself and Jayaraman. This is 2016. Yeah, so what it means is the following. A hash of Rn plus intersection range of A contained in Rn plus. X non-negative, X belongs to range of A, then A hash X is non-negative. This generalizes A inverse non-negative. A inverse non-negative means what? A inverse Rn plus contained in Rn plus. A hash itself is non-negative is not true. That's a bigger requirement that will not be satisfied. You can verify this example. A hash is a multiple of A here. For this matrix, A hash is a multiple of A, and so it can't be non-negative. Okay, so A hash non-negative will not work, fortunately or unfortunately. A hash non-negative you will not get, but A hash is non-negative on its range is what comes out. So I stated this result for you to compare this with the invertible M matrix case. A is an invertible M matrix if and only if A inverse is non-negative. A is an M matrix with property C if and only if something more general than the inverse, which is the group inverse. By the way, why not the Moore-Penrose inverse? Moore-Penrose inverse doesn't work. Group inverse seems to be the appropriate extension for an M matrix with property C. So group inverse exists, and that it is not non-negative, but it is non-negative on a subspace. That subspace is given by range of A. And the meaning of that is this. You must compare this with the meaning of what is A inverse non-negative. A inverse non-negative is this statement. So this is more general than this. Okay, so I'll stop here. Thank you. Any questions? Yeah. Applications, as I told you, whenever T is a transition probability matrix, the group inverse tells us how it progresses. The group inverse always exists. By the way, this is an M matrix with property C. See, I just gave one numerical example. This is an M matrix with property C, but there is a class which is this. You take any transition probability matrix and then look at this. this will always be an M matrix with property C that can be shown. That's what Clemens did. So this is a huge class. Just as how you have Ri minus B, B non-negative, R greater than spectral radius of B for invertible M matrices, this is a huge class of M matrices with property C. Yeah, so there is this interpretation of how the Markov process progresses in terms of the entries of A hash. The details are in that paper, Mayer's paper. Any questions?